places. Like 4.2 or 1.8.
Yeah, as far as the book goes, or as
Yeah.
far as the
As far as like
CED goes.
the book, I think.
I think it's 4.7.
Okay.
Basically, I think this is, or maybe it's 3.7. I think it's 3.7, and then L'Hopital's is 4.7. So like, this is the unit of the sevens. Because related rates is 2.7. This is 3.7.
Oh, okay.
That's 4.7. Basically, it's all the things that get like tacked on at the end of chapters that like are just kind of weird things. So we just put all the weird things together in one unit instead. They're also all of our contextual applications, which is what Unit 4 is for the CED. Alright, but linear differentials or linear approximations is what we're talking about today. Do we remember doing it?
Yeah.
Ish?
I remember approximations.
Okay. We didn't spend a ton of time on these, just because they don't come up a ton on the AP test, and two, they're pretty straightforward. However, we are going to spend a little bit more time on them today, just because there's a couple of things that I want to talk about that are going to help set us up for some of the future things that we do. Because some of the other things that are BC topics only are kind of related to this process. Does that kind of make sense? Yes or no? Alright, so what is a linear approximation? Or a tangent line approximation? Like in your own
Approximating
words.
a close point using the tangent line instead of the graph itself.
Cool, yeah. So like my picture here, right? If I have the tangent line for my graph, okay, that's F at point A, right? This line is not my actual graph, agreed? But what we can do is say that this graph is not a fun graph or not a fun like equation to plug into. I can then take my tangent line and use that to approximate some other value x. Yes, no, maybe. Are we all okay with that? And I did like the word that Andrew used as far as it does have to be close, okay? Because the farther out I get from my original A value, the worse my approximation is going to be. Yes, no, maybe. Or we can't guarantee that it's going to be close. So we do want to pick values that are close to our original tangent line. So what we can say is L of x equals, and basically we're just setting up a equation using our tangent line. So it's really just our tangent line equation. So we have f prime of a times x minus a plus f of a. And we can use this to approximate some x value close to a. Yes, no, maybe.
Yes.
Now, the thing I think we talked about it vaguely, but we didn't give it like quite as much of a like full-blown definition as we are going to now. Right, my original function is f. Yes. So what is this e thing? Has something to do with the approximation. So notice that this point, right, would be my approximation of x. Yes?
Oh, it's how far away.
Deviation.
Yeah.
It's how far away it is.
Error.
Agreed. So my E stands for
Ah.
error. Okay? That is basically how far away my approximation is from my actual actual value that we would have gotten there. So how would we find that? Like in general.
Calculate the two.
What?
You would calculate both of them and then subtract.
Okay. So, but like, do I care if it's positive or negative?
No.
No, right? Like I just want to know the distance between the two. So I'm going to take the absolute value. So it is our exact value minus our approximation.
Why would you approximate if you could already find the exact?
In this case, we probably wouldn't. However, later on, we're going to be dealing with like other types of errors.
Okay.
But like what this can be helpful, right, doing is sometimes we don't necessarily want to know what this actual value is, but we do want to know if it's like smaller than a particular value, right? So like sometimes it can be helpful to say, I know that my error has to be less than 1/10, or I know that my error has to be less than, 1/1000 or something like that. So we won't necessarily always find this value, but sometimes it can be helpful to set up an inequality so we can state like how close our approximation has to be.
Okay.
Does that kind of make sense? So like for right now with this, we will be just like using our calculator to find out what the error would be, but for like other things we do, we still need to like have this idea of what an error is.
Would that be formatted as like the plus or minus 1/10? Would it be like x plus or minus error? Or is that just for like statistical applications?
Oh, for like an error bound, yes.
Okay.
We will format it like that.
Perfect.
We're not there yet, but we will format it yet. Yeah, we're going to be approximating other stuff in this class. Then let's call it error bound. So in general, if I use what I did up here, what would our formula be? The absolute value of, so my exact value would be
F prime of x?
Yes, f of a, right? Like where I could actually just plug it into, no, not a, but x, right? Because I'm approximating some other value besides a. I'm using a to approximate that other value. Yes or maybe? Are we okay with that? You could put a b there if it makes you happy. Just don't put a's because I don't want you to get confused with the a's that we're already using. Minus what?
L of x?
L of x, yeah. Whatever we got when we plugged in that value into our approximation. Is still ready?
Yes.
Questions? Oh, fine. Got some examples?
Will it always be given which value we should approximate from?
I would say that usually it's going to say, one is either going to give you information, like this one, or like a table to where I don't have very many choices of what I can use. If it gives you a function, yes, usually it's going to tell you what it wants your a value to be. Otherwise, it would be something like really obvious. Like if it says approximate 0.1, I'm going to use 0 as my original a value. Does that make sense? So, but I would say like most of the problems I've seen, it gives you something like that it wants you to use. I'm not going to say always, because like I haven't looked at like all of the different things, but I would say like most of the time, yes. So it says that this function f is twice differentiable, where f of 3 equals -2, f prime of 3 is 5, and f double prime is 3 equals 1. Write the tangent equation of the tangent line, and then use the equation to find the value of f of 3.1. So what are we going to do? Write the equation. All right, so it might just be helpful to start with our just like formula, right? L of x equals, what's my a value this time that we're using? 3. So that's the information that they give us, right? So I have f prime of 3 times x minus 3 plus f of 3. Yes? Okay, what's my f prime of 3? 5. Okay, x minus 3. Okay, and then what's my f of 3? Negative 2. There we go. Okay, so that would be my tangent line for my approximation. And we're going to leave it like that. Because it's actually really helpful to leave it like that. Because remember that we are going to approximate something that is close to whatever my a value is, right? So this subtraction right here is usually going to be pretty easy to do. And so it's helpful to leave it in this form. So 3.1 minus 3 is 0.1. If we left it like that, would we be okay? For a free response question? Yeah. Okay. Otherwise, how could we rewrite that?
Negative 1.5.
It is negative 1.5. How do we get negative 1.5?
5 times 0.1 is 0.5.
Okay.
Minus 2.
Yep.
Minus 2. Yeah.
So we just left it in decimal? That's fine. What is 0.1 also?
1/10.
1/10, right? So 5 times 1/10 would be 1/2. Minus 2 is negative 3/2.
Yeah.
Cool. So they gave us this thing about the second derivative. Do we care about that?
Maybe for finding error.
Oh, if it's above the.
Yeah, so like in this case, it doesn't ask us anything. So like for this particular problem, it was extra. But yes, if it asked, is your approximation an over or an under approximation, remember we do need the derivative or second derivative for that because your under and over approximation depend on what? Concavity, right? So remember that in this case, this at 3, we would be what? Concave up, which means that our approximation would be a under approximation. Versus if it's concave down, it's going to be an over approximation. Like I said, in this case, it did not ask for that. So for this particular problem, it was just extra information. But sometimes it will ask you, is it an under or an over approximation? What questions do we have there? Okay, moving on. So this one is calculator active. So consider the equation y equals sine of x at x equals pi over 3. So a place that we will see linear approximations come up a lot is our transcendental functions, meaning our sines, cosines, and e to the x's. Because all of those are ones that we don't get nice pretty numbers for, right? Like those are ones that are harder to like plug in to, and so that's why we tend to use some of our approximations for this. So it says we know the ordered pair corresponding to this angle is 1/2 square root of 3 over 2. Since the angle is approximately 1 point stuff, let's write the linear approximation for x equals 1.05. Yes, no, maybe, so. So we're using, okay, this as my a value. Are you with me? They gave you the approximation here, basically just to show you why we're approximating 1.05 is because 1.05 is fairly close to pi over 3. So it's an okay number to use as our approximation. So what are the things that we need? Yeah, we want our tangent line approximation, so L of x. What are the 3 things? It's 2 things. What are the 2 things we need to write any equation of a line?
Slope.
Point and a slope, yes? Okay. Do they give us a point? Yeah, that's nice. Could we have found our point with that angle? Or should we have been able to find our point with that angle?
Yes.
Yes, but if we didn't, then we're okay. Which one of those values am I using? Is that my point that I'm using? Am I using 1/2 square root of 3 over 2? No, what's my actual point that we're using? What's my x value? Pi over 3. So then which one of those is my y value? Yes.
Yeah.
Because from our unit circle sign is our y values. Yes, no, maybe? Are we all okay with why I chose that one? Okay. So what's the other thing that we need? A point and a slope. So what do we need to find? A derivative. What's our derivative? Cosine of x. Yes? Are we okay with that? So then what is it at pi over 3? 1/2. The other one. Yes, no, maybe? So then what's our approximation? L of x equals 1/2 times
X minus
we're all okay with how we got that.
Yes.
Now what are we using that to approximate? And that's why this is calculator active, because these are not going to be fun numbers. So we're just going to plug all of that into our calculator. And what do we get? Someone typey for us. What do I need to make sure we're in? Radians. What do we get?
0.867.
Yeah. 0.867. You should get that.
Well, if that's what we're supposed to get, then I'm going to double check it.
So then, my next part asks us to find the error of our approximation. What do you think? So what would I need? Okay, the exact value. So I have the absolute value of f of what? Yeah, which in this case we found it was 1.05. That's what we used to approximate. Minus our L. Alright, because we're trying to figure out what was the difference between our exact minus our approximation.
Are we going to do percent error
Okay.
on the test?
Not on this one. But we will later. Right, your percent error would just be exact minus approximation divided by exact times 100. Right? Or your percentage, if we wanted to find it. What do we get? It is a really tiny number, so what is it? How many zeros do you have?
Like after you do the decimal?
Yes.
5?
Yes.
Okay. Then 3, 4, 0.
Did anyone get anything different? Or is that what we got?
I mean, I got an answer using the rounded number, but not using the original number.
I have the answer with the original function and not the rounded approximation.
Yeah, either should be fairly close.
Because the one I got was like 4.232 times 10 to the negative fourth, which I think is slightly off.
Right, so for sine of 1.05, let's make sure mode I'm in radians.
Sine of 1.05.
Okay, that minus 0.86.
Yeah, you said
I said 340.
340, and you used the exact.
Mhm.
Okay, that's right. It's off a little bit. That's fine. So you said 340. Yes. No, maybe.
You said you put that into the original? So, sign it?
Yeah. 1.0 sine of 1.05. But make sure your calculator's in radian mode.
You need to put that up.
The zero is not necessary.
Wait, I'm
So like if we wanted to, so like I said, a nice way to talk about this is what we know that our error is to say less than, because that's a really odd number. Yes. So what's another way that we can write that?
Sine
So like if I wanted to move this back over, right? If I put this in like say scientific notation, yes?
Yes.
Mm-hmm.
Okay, that would be what? 10 to the
Negative 6.
1, 2, 3, 6, yes?
Mm-hmm.
But let's think about, yeah, if this is 6, would get me all the way to 3 point stuff, yes?
Mm-hmm.
Right, 10 to the negative 6. However, we can't say that it's going to be less than that because I don't know that it's less than the actual decimals that I got there. You with me? We can only count it basically up to before that, like where my zeros stop. Because we know it has to be smaller than 10 to the negative 5th, because I know it's going to be accurate up until that point, up until like my 3 starts. Because some of us got 3, some of us got 4, right? So like depending on which one you use, the rounded or the non-rounded. But I do know it's accurate up until that, right? And so I had 10 to the negative 5th there. So basically I can just use my zeros to say then my error had to be less than that at least, which is a pretty accurate number, yeah? Yes, no, maybe. What questions do you have about that? That one's pretty similar. It's just the 2 to the x. That one's the 2 minus. I want to get to this one because I want to look at using a table.
I think we have 2 minutes.
Hmm?
I think we have 2 minutes.
Okay. Well, so we'll finish it up tomorrow.
I was just about to say one more.
Do we? Don't we go longer on this? Oh, no, it is 1 second. Yeah.
Okay, I was like, I thought we had time to do it. Oh, okay, I was like, I was skipping over some of them because I knew we were like pressed on time, but like, I thought. Okay. I didn't think we were that far off. Alright. So it says let f be the function that is differentiable for all real numbers. The table below gives the values of f of x and its derivative f prime of x for selected values in the interval -1 to 1. The function is concave up on this closed interval. Write an equation of the tangent line of the graph where x equals -0.6. Okay. What do we think? Okay, let's just write out the full formula first. So we first have f prime, right, of negative 0.6 times x plus 0.6 plus just our f of that. Are we okay with that? Like, I would be careful just jumping straight into values from this, just because there's a lot of values, and make sure you're not using the like function value for this and that sort of thing. So what is my derivative at negative 0.6? Negative 2. Then what is my y value at negative 0.6? Negative 51. So are we all okay where we got that from? So now we want to use this to approximate, yeah? So what are we plugging in? Negative 0.5. Should we be able to do this one without a calculator?
Depends on how awake we are.
So what is negative 0.5 plus 0.6? 0.1. Yes? Okay, and negative 2 times 0.1. Wait, ready? Yes. Okay. Minus 51.
Negative 51.3.
Oh yeah, we can't do this one in our head.
Okay. I was like, I feel like y'all are making it much. What?
Not 0.
Oh, sorry.
We can't do this in
There you go. No, I mean, he might have said the right thing. I might have just brought down my 0 by accident. That's okay. Yes, no, maybe?
Yeah.
Okay. Because that's a pretty valid one to do without a calculator. However, if it's a free response, we totally could just leave it right here. Right? Like, not a big deal. Okay. But then my last question is this approximation greater than or less than the actual value of f of negative 0.5? Less than? Why? We're all okay with that. What questions do we have?